Hi guys, this is Sampling Distributions Part 3. The first thing I want to do is a follow-on to Sampling Distributions Part 2. And I left a question right at the end that we're going to answer right now. And it was, let's assume that we have a population with a p equal to 0.98. What must n be for us to achieve normality with a sampling distribution? In other words, the question is asking, how big does n have to be in order to meet the rule np greater than 10 and n times 1 minus p greater than 10? We have to meet both of those rules in order for us to achieve normality. So this is going to be simple algebra. The really tricky part of this is that sometimes when people do these problems, they don't realize, like I said in part 2 of this video, they don't realize that they have to check both the p-value, the proportion of the population, and its complement. Let's go ahead and do both of those. So we have np must be greater than or equal to 10. I have n times 0.98 greater than or equal to 10, and I'm going to solve this. I'm going to divide both sides by 0.98. So I get n must be greater than 10 divided by 0.98. Well, I did this a little bit earlier, and I think what I got was, if memory serves me right, that means that we would have 10.204 or so, and you know, clearly that's not a hard threshold to meet. The only thing a statistics student or statistician wants to remember here is that, you know, you can't have 0.2 of a person. So we need to actually have a value that is equal to or greater than that. So that ends up meaning that we need 11 people to satisfy this side of the equation. But we're still not going to have normality in this case. Why? Well, it's because we also have to check the complement of our population p-value. That means that we have to check 0.02 also, and I'm going to do that next. Okay, let's see if my studio lights stay on this time. So we have n times 0.02, and that has to be greater than or equal to 10 also. Dividing both sides by 0.02, I have n has to be equal to or greater than 10 divided by 0.02, and that is 500. So in a case like this, where we're coming up with two figures, we have to go with the greater value. Remember, whether we decide that p is equal to 0.98 or p is equal to 0.02, one man's success is another man's failure. It's really kind of arbitrary which side of that proportion we consider to be success. We're still going to have to achieve normality with both our p-value and its complement. Well, you know what? I'm not fighting with that stupid light anymore. It's rechargeable. I'm going to recharge it. I just recentered the board, and we'll just go on this way. Let's do another problem. Let's continue with this, because I promised you some problems with sampling distributions. And we're going to do a few, okay? Here's a scenario. We have mu equals, what do I want mu to be? 100. I'm looking at my notes over here. Mu equals 100. Let's make the standard deviation of the population 9. And we will choose a sample size of 324. Now look, whenever you're starting problems that involve any sort of the things based on sampling distributions, you're going to have to sort of keep your head on straight and analyze things carefully and correctly from the beginning. This is clearly going to be the distribution of sample means, because we're talking about the population mean and the population standard deviation. It can't be otherwise, so do not use the wrong formula for the standard error, okay? That is not the formula that we want to use. Okay, make sure you're using the right, on tests and so on, and in projects and just work in general. People miss this sometimes, and it's the wrong place to lose points. It's easy enough to use the right formula. And another point I want to make right at the beginning. Anytime you're doing anything involving a distribution of sample means, in other words, if you're doing statistics where somebody says a sample of such and such size, or the sample mean was, or a group was measured, anytime you see those keywords, sample, sample mean, group, sample proportion, and so on, you want to think, oh, I better get ready to use the distribution of sample means or the distribution of sample proportions, and I'm going to have to get the standard error. So even before I pose this question, let's calculate that standard error. The formula for the standard error of a distribution of sample means is sigma divided by the square root of n. In this case, that's going to be 9 divided by the square root of 324, especially right at the beginning. I like to use perfect squares because it just makes stuff easier. So we have 9 over the square root of 324, that's conveniently 18, or 1/2. That's our standard error. So we're going to use that. So our standard error, sigma sub x bar, is 1/2. And just for the record, the mean of our sampling distribution, mu sub x bar, is 100. Okay, good. So now we're ready to take a look at what the question is, what we're being asked. What is the p, the proportion or probability, if you like, of sample means between 98.5 and 101.5? This is an interesting question. We can get a lot out of this. We're going to solve it in just a second. It's relatively easy to solve, but I want you to notice something. In the original population, with a mean of 100 and a standard deviation of 9, we have, let's see, from 82 to 118. I'm trying to go from the mean. I'm mentally doing it. Should have written it in my notes to begin with, but I didn't. I'm going to the left on the number line, 2 standard deviations. I'm going to the right on the number line from the mean, 2 standard deviations. Now look at that. Inside that span in the original population, not the sampling distribution, the original population, inside that span, we're going to have 95, as it happens, the empirical rule tells us it's 95%. It's actually about 95.44%, right? If you look it up on the table and I'm not mixed up, it's going to come out 95.44%. So across this span, which is 36 units wide, we have 95% of the original population, assuming it's normally distributed. Now, with this question, when we're talking about samples, all of a sudden I'm being asked about a much narrower span. And that's important to notice. When you're using samples, the curve that represents what you're working on gets much, much, much narrower. The standard deviation of the population is 9. The standard deviation of the curve that we are now working on is 1/2. That's the standard error. We're working on the distribution of sample means, and it's much narrower. Let's go ahead and find out the z value of these 2 points. If you plug it into the z value formula that's appropriate in this situation, I think you're going to find that the z value of this, in fact, I'm wondering if I shouldn't just stop for a minute or give you a second to calculate that on your own. Why don't you pause the video if you need to calculate that on your own, just to make sure. Okay, we'll go ahead and I'll put it in here. I'm hoping you got -3z and +3z for these 2 points. So this question asks us, given the scenario, what is the proportion of sample means, not individuals, but rather samples whose means are between 98.5 and 101.5? We're going to answer that because we know that this is going to be normally distributed. Look at that look at that sample size, 324. Assuming we're meeting certain rules, which I didn't bother to mention in the first video, but you can find them in your stat textbook, or it's fairly easy to look up. It's not part of the conceptual part of this. As long as we meet certain rules like sampling is truly random and so forth, we know that this distribution of sample means will be normally distributed, because that is way bigger than 30. So I can rely on the normal distribution table to give me this answer. If I or you look this up on a table, you're going to find that the area of a normal distribution between negative 3z and positive 3z is, as accurately as the table can give it to us, 99.74%. So, whereas in the original population, we had a little over 95% within a span of 36 units, here, within a span of 3 units, we have 99.74%. So, the act of taking samples and bigger samples tends to narrow the curve that you're working within, that you're working with, tends to narrow it, sometimes very drastically, in towards the mean of the distribution. So that's the answer to that. Okay, we'll go on to one more question. We'll go on to a few more questions, but the next one I'm going to write out first, talk to you about it, talk to you about the setup, and then solve it. Here's our next question. Assuming we have a population whose proportion is 0.63, and we are taking samples of 28, we're imagining that to be our sample size. And just incidentally, if you have an impulse to tell me that that's not going to guarantee us a normally distributed distribution, I want you to check it. Check it and send me a comment if you want below. I love to see those. It makes my day. It makes this whole YouTube thing 20 times more fun. Go ahead and do that. I think you'll find, if you apply the appropriate rule, that we do have normality here. So here's the question. What is the probability, what are the points A and B such that the probability or proportion of sample proportions found between them would be 90%? Now that's kind of complicated, but I'm here to lead you through it, and we're going to work on it anyway. You might read this question as a test question somewhere, written out. Find 2 points such that the proportion of the sampling distribution found between them, meaning the proportion of p hats in this case, would be 90%. Now I'm going to add in a few more rules here. This is kind of redundant. We don't really need to say that A does not equal B, but I'm going to say it anyway, and I'm going to say it this way. A is less than B. So we know that the sequence that they come in, just to keep things organized, right? There is no solution for this if A and B are allowed to be the same number. And we also want to put another, because there's infinite solutions unless we put another set of rules on here. And I'm going to do this. I'm going to say the absolute value of A minus the population proportion is equal to the absolute value of B minus the population proportion. What does that obligate us to understand? Well, now it's saying that the distance between A and B from the population proportion, which incidentally is also mu sub p hat, isn't it? It's the middle of our distribution. That's telling us that they have to be symmetrical around those points. That's the only way that this can be solved. So what we're trying to do, and I'm going to draw a picture of what we're looking for now. That's still on our test sheet ahead of us, or on our work paper ahead of us. I'm going to erase it to make more room and draw a picture. We're being asked this. Here's mu sub p hat, and here's A and B. And I want to know what A and B are in this situation, such that this zone, there goes my light again, this zone is 90%. I don't think I got the warranty on that thing. So what are A and B in this situation? Let's figure that out. Now that we understand the problem, we are going to have to find the standard error, sigma sub p hat. That's going to be the square root of p times 1 minus p, let me write it in, over n, okay, 28. I worked it out. I got 0.091241. You should do it and get the same thing as I do. That's important. Let's make sure that we agree. So I know what the standard error is now. I'm going to record that over here. Sigma sub p hat equals 0.091241. Okay, got it. Next, we got to figure out what the z-value is that we're going to use. I'm drawing a curve again. Remember that we want 90% in this middle area. That's what the question dictates. So I need to find out what this z-value is. The way to look at it, remember, mostly tables will show you cumulative values from the left. So you can either look up the positive value that gives you 90 plus the tail area, or we can just start out by looking, remember it's got to be symmetrical. We can take a look at the table to immediately get the negative z-value that's going to be over here after we figure out how much area has to be in this tail. Let's keep this straight because it's easy to make mistakes here too if we're not careful. There's 90% in the middle. And the whole thing going from infinity in this direction to infinity in that direction is 100%. So I know that if there's 90 here, there's got to be a total of 10% in the tails. If there's a total of 10% in the tails, then that means there's got to be 5% in each one of the two tails, because again, this thing is symmetrical. So I can look up on the table and just find out what z-value, negative z-value, gives me 5% in the tail. And if you look it up, you're going to find values pretty quickly and possibly be confused. Why? Well, there's a value there that works 1.64, and there's another value there that works 1.65. And the problem is they are both about right. They're both pretty close. One of them gives you 0.0505 in the tail, and I guess the other one gives you 0.0495 in the tail, if memory serves me right. And so you're sitting there going, okay, which one do I use? The truth is, a lot of stats classes, especially, like introductory stat classes, you're going to find that the instructor doesn't really care that much. Sometimes they're going to give you some sort of direction. Let's see if that stays on. What I like to do is just say, okay, for this value and certain other cases where we have to split differences, let's just agree to go with the mean. So I'm going to use 1.645. So we'll call this z equals positive 1.645, and this as negative 1.645. And that's what we're going to go with. So now we got to find those 2 points. We have just figured out that these two symmetrical points are each 1.645 z's, or 1.645 standard errors away from the population proportion, or if you like, actually more correctly said, mu sub p hat. And they're symmetrical. So this is to the right, 1.645 z's, and this is to the left, 1.645 z's. So what we got to do is, it's actually pretty simple at this point. What I'm going to do is I'm going to take that mu sub p hat, which is also the population proportion, 0.63, and I'm going to add 1.645 for the standard errors times, for the z rather, times the standard error. That's, I'll leave off the leading zero now, even though it's not really good technique. So that's going to be my right-hand point. So I made an error. My left-hand point is going to be subtracting, isn't it? I'm going to go from this point on the number line leftward, 1.645 z's. And by z's we mean multiples of the standard error. Those 2 points will be our solutions for A and B. Let me reverse that too. This is B, and that is A. Try it out. You'll see that that's correct. I'll come back with the solutions. I got these 2 values. I got A equal to 0.4799, just to give you all the digits, 0.8555. I'm sure that even that is rounded. There's more digits out there for you to solve for if you wanted to. And B is 0.780091,445. Okay, so there's our 2 points. So what that means is that we have, and I'm going to round to 0.48 and 0.78, we have the proportion of this distribution between 0.48, close enough, the proportion of samples that have proportions between 0.48 and 0.78 in this scenario is 90%. So 90% of all samples in this population, when our sample size is really pretty small, 28, 90% of them are going to be between these 2 numbers. And that's going to start to give us a hint about how they do political polling statistics and demographics. They use techniques really close to this that we're going to be going to pretty soon, actually. You want to learn this problem well, because that's going to be vital. Let's do another one. Let's do one more problem for this video. Let's imagine a casino. I'm in the mood for gambling. Every time I turn that light on, I'm gambling. So it put me in the mood. Let's say there's a casino where the mean value of a transaction for a customer visit is negative $250. What I mean to say is, every time a customer comes in, the average loss for customers is $250. I have no idea about actual gambling mathematics. I never worked for a casino. I imagine that it may not be that different from this. I'm going to give you general sorts of numbers that I find plausible. So we're going to see how they work out. On average, in casinos that stay in business, customers lose. Some customers win big, some customers lose big, but on average, when you balance out all the big transactions and the small transactions, positive and negative, there's a net average loss to the customer, or else they wouldn't stay in business. So the mean transaction value for each and every customer's visit at this casino is negative $250. Let's say for this population of customers, the standard deviation is, let's make it 600. It is possible for us to have a really big standard deviation because we don't need to worry about having a value that is not allowed to be, for example, in this case, positive. People can walk out with net profits. That's okay. You could be $1 million in the negative or $1 million in the positive direction. So it doesn't really shake our sense of plausibility here that the standard deviation is actually a bigger value in absolute value terms than the mean is. That's okay. And I think a casino would want a fairly big standard deviation. They hope for that because they want to see people winning periodically. They want to see that. They want the whole floor to get excited and to start ordering more drinks and everything. Because as long as the mean is the same, they're still doing the same. This just means if you have a bigger standard deviation that a few people are winning bigger and a few other people are winning even more badly, losing more badly, that the dispersion of value figures is more broad on the number line. But again, the casino's only concerned about the mean. So I think those numbers are relatively plausible. Let's take a sample of 50. So we got 50 people. I know what you're thinking. They're older folks. They're on a bus. They're going to Atlantic City. They're going to gamble away that check. So what we're going to do is figure out how that bus is going to do. In fact, more specifically, I want to figure out what is the probability that the mean of this bus in terms of transaction value is at least 0. What is the probability that these 50 seniors on their bus going to Atlantic City, what's the probability that on average they just won't lose? I'm not even talking about getting enough money to pay the electrical bill. I just want to make sure that these old folks don't lose. What is the probability of that happening? Well, the first thing we have to do, as I mentioned before, is figure out. Now, you've got that on your paper because you're following along, I hope. First thing we got to do is figure out what the standard error is. So the standard error is going to be sigma divided by the square root of the sample size, which is 50. Now, when we do that, we get about $84.85. I think that's what it came out to. There's a few more decimal points that follow. Remember, these are dollar figures, and that's our sample size. So that's the first thing we need to know. So I'm going to write that right here. Sigma sub x bar is equal to $84.85. Close enough. That's a rounded value. Let's make sure we understand this question. You cannot be too much with the drawing of the pictures when you're trying to figure these things out. I've drawn only the right-hand side of the distribution because that's going to be enough for us. We know that the mean of this distribution is negative $250. That's also mu sub x bar. And what we want to do is figure out what proportion of this distribution just peeks its head up above 0. That's still for samples of size 50. So what we got to do is figure out the z-value of 0. So I'm going to plug in the numbers and let's figure that out. We're figuring out the value, the z-value for 0. I'm going to subtract my mean. Notice how I'm being careful with the signs. That's another place where sometimes really good mathematicians and math students will make an error. It's easy to make sign errors. Don't do it. And I'm going to divide by my standard error. If you're working this and you still have the standard error value with the various digits following to something on your calculator, you may as well hold on to it, store it into memory, or do something rather than truncating it, because you'll get a slightly more accurate value by doing it that way. At any rate, I work this out. 0 plus 250, which is just positive 250, divided by 84.85. And I get z equals 2.95. So that's a fairly high z value. If you go into your z table and you look up the value to the right of 2.95z, or if you want to, the value to the left of 2.95z, and then subtract that from 1, you're going to find that the area in this tail is 0016. That means 16/100% of groups of 50 are going to end up net not losing at this casino. And that's the way gambling works. Okay, guys, please let me know if you like those questions or you want more. Do me a favor and comment at the bottom. Like I say, I mean, it's fun. I like it. And I'll see you next time.